Cool.
Welcome, Kevin.
Thank you.
Yeah, thank you. I think maybe what would be interesting is I try to start it off just with like a little bit of like historical context. We met in Spain through our mutual friend. Yes. Shout out Laura, and just kind of nerded out on like different blockchains, the different architectures, and just had a really good conversation. And now back in Miami and ready to roll.
Yeah, shout out to Laura. Indeed, it was actually that conversation that made me convinced, because I tend to stay away a little from podcasts in general, because they're either from like investor crowds that I don't really know anything about, or from like people that try to be technical but they're not quite technical. So when we were having the conversation in Barcelona, I was like, this guy's asking some good questions. Maybe we should just redo all of this thing all over for a podcast. And it's perfect for all the people that have been asking me questions, and I've been relentlessly ignoring them on Twitter because it's just not a good medium to respond like subtly to technical questions. So,
no, not at all. It's hard to debate or talk about the nuances of blockchains in 280 characters.
It's really hard. I mean, people go to like graduate school and they do like 5 years and 6 years of distributed system studies, and it's been going on for, at least 40 years. 40 years, 50 years of this kind of stuff. And you can't distill it to some guy that saw something. It's the equivalent of when, which I fell in the same trap, by the way, when COVID happened early, and now everybody started becoming a virologist all of a sudden. And you can't really just I became a virologist too, quote unquote. I basically read a few blog posts and a few Twitter things. I was like, oh yeah, that makes sense.
I totally got this.
Yeah, I got this. I am an expert now. And I bet this is exactly how the virologists were thinking, like reading all of this, and they were like, what the hell am I looking at? And so I can't really blame the reply guys for like, they mean well, but there's a lot of like subtle information here, and you really need a long form, high signal place to talk about this.
I couldn't agree more. Yeah. And that was kind of like the whole impetus between trying to do the podcast and trying to do it to the best of my ability. So learning on each one, learning about the cameras and the mics and all that, been a little bit of a journey, but each one's getting slightly better. So again, thank you. I really appreciate it.
Absolutely.
Maybe like an interesting point to jump off of is just like how you got into crypto. Because I think like everybody's story about like how they first got into blockchain is super unique, because now there's so many different avenues to get into crypto. How'd you fall down the rabbit hole?
I'm technical by background. I got into crypto on a serious level, I guess, during my late undergrad and graduate studies, especially when literally my thesis was on how we build fast and scalable distributed systems, which is the topic of discussion here. But before that, I was into crypto kind of like passively as just somebody that was interested in Bitcoin. I got into Bitcoin, got into it as in like, I knew about it, and I did a little bit of Bitcoin mining like in 2010, and then kind of like stopped doing it, and then got back into it from a technical perspective. And I think I got back into it it was a hiatus from 2010 to 2013, and then 2013 I got back into it after I started attending a few like more of the dev conferences.
That's early. Were you? Did you do mining on CPU?
I did mining on CPU.
Dude, all the OGs, they tell me they started mining Bitcoin on a CPU. I'm like, oh shit, that's how you know you're early.
Yeah, it was very early. It was when Bitcoin was it was so early. There was no market that I knew, or at least I didn't know about it. Yeah. So you would just get these things in your wallet. It was like this C++ thing, and you just see these things that would just appear every now and then. And like, okay, now what? Like they were worthless. I had no idea how to sell them or anything. So I was running on a Lenovo box that I ended up at some point reformatting because I just was screwing up with the BIOS settings, trying to like figure out how to hack this thing. Just playing around with it, and then I literally couldn't boot back into my machine. Oh no. And I was like, I don't know how to fix it. So I just reformatted the whole hard drive. So I lost all those Bitcoins.
I can't imagine like how many Bitcoins have actually been lost or those private keys. Like,
oh yeah, for sure. So much. I wouldn't be surprised if like 10% of the supply probably has disappeared forever.
Oh yeah, 100%.
No one can find it.
It's wild. So after that, like 2013 timeframe, were you still doing your studies?
So yeah, I graduated college in 2015 and then immediately went to grad school. And right before that, I was doing some programming languages and some cryptography stuff, mostly cryptography stuff. And then it was a natural transition where I, started like thinking about, okay, I obviously had the interest in cryptocurrencies, but it was like, I'm not really interested in the economics aspect of it too much. It was just more of like, we can probably do something better here. And so I started working on distributed systems research at Cornell, and
that's awesome.
And then eventually, yeah.
So was that pre-2000? So that was that before or after the 2017 bull market? Because that's when I got in and was like, what is all this stuff?
It was before. It was when Ripple was kind of like getting started as well, and Ethereum was just getting started at that time. And in fact, like I remember like the first few years of my grad school at Cornell, like Cornell was like a hub because Emin Gusir was there, and Vitalik and the rest of the team would come to Cornell. We would have every summer the Ethereum bootcamp, which was one of the best boot camps. It was so fun. It was like maybe 100, 200 people, maybe slightly more, would come in at Cornell for like a whole week.
Jealous.
and just hack around and talk research and things. And it happened every year and over the summer, and it was just awesome. It was the partnership between Ethereum Foundation, I think, and the IC3, the Initiative for Cryptocurrency, something. It's a academic institution thing, and yeah, it was just great. And so I was exposed to it early on. And at that same time, 2016 until now, I've just basically been working on like deep distributed systems work. Well, not these days so much, but deep distributed systems work on like how do we build scalable blockchains.
That's amazing. Yeah. I'm super jealous. I wish I could go back in time and attend those events.
Yeah.
All the people that have come from Cornell that I've spoken to, especially at the AVAX event, I've been blown away by their engineering capacity and just the level of depth and knowledge that they have about blockchains, and just their openness also to answer my questions.
We're super lucky. We got a good crew there.
So so that was prior to 2017. The bull market happened in 2017. I was one of those noobs at the time that didn't know too much and thought I was going to kill it. And then obviously 2018 happened and a lot of coins went down like 95% plus. So after that bull market, maybe just kind of walk us and like the listeners through kind of like what you're working on at that time and just like your version of the events.
Sure. So, I mean, I wasn't really super affected by the bull market up and down. It was just another market. And we just continued working on Avalanche, the core protocols. At that time, 2017, 2018, we were doing prototypes in C++, and just kind of like seeing the performance and all these kinds of things. And then 2018 and afterwards, we started, talking about it publicly and all that stuff. So
that's awesome.
Yeah.
And Avalanche officially launched towards late 2021, correct?
2020. So
2020,
September
sorry.
of 2020. Yeah.
Okay.
Yeah.
Nice.
Right before the fall 2020, the rise of Bitcoin again. So,
yeah. No, it's
been a while.
It has been.
It's been a while.
Maybe before we jump into the specifics of Avalanche as a whole, from your point of view and like all your background and your studies, maybe just touch upon like how you would describe a blockchain more holistically.
So that's a very subtle question, and I think a lot of people are completely maybe confused around even what a blockchain is. A blockchain is a complicated thing. It's not just a data structure. Well, I mean, a blockchain is a data structure. It's just a chain of blocks, where each links to each other and with the hash on the previous one. But the more important thing is, what does the blockchain mathematically represent? Because if you cannot understand the mathematical representation of it, we can't really understand how to model it as a computer program. Everything in a computer program has to be a mathematical representation. That's just what it comes down to. So from I think what really helps to understand eventually the discussion of where are the scalability bottlenecks with blockchains and all that things, I think it really helps out to think about blockchains in the good old Gedanken experiment form of just like, what is the simplest possible mathematical model? And then let's kind of increase in complexity. And then using that model, I think we kind of start figuring out, okay, here's where the bottlenecks of this thing are. And so what is a blockchain? Well, before we have to answer that, we have to answer the question of what is a computer. A computer is a machine. It's a state machine. State machine meaning that it has some memory and some data on that memory, and it takes in inputs. It processes the inputs based on some instructions, and it updates the data on its model, on its internal state. So if we want to start understanding scalability concerns here, let's kind of like think about where the bottlenecks are from the simplest point, which is, suppose that we have a magical machine, which is a computer that has, just thought experiment, a computer that has infinite memory. It doesn't have storage, it just has infinite memory.
Okay.
And it never goes down. It's a magical computer, right? So it's a network. So it has a network. It has messages that come into it, and it can respond to messages. It can compute data on those messages, and it can write things to its memory very fast, and that's it, right? So if we had that, then we technically have the very fastest thing we can possibly build from a processing perspective of any state machine, right?
Because it's all stored in memory.
It's all stored in memory, and it's one single machine. It's one single machine. Data comes in, it processes it, it takes out the data. Now you can do all kinds of optimizations. Maybe it takes the data and it does some, we were spoken in Barcelona, it does some like parallelization on the data. But at the end of the day, because it has a state machine which is sequential, it has one instruction after the other, there is a fundamental limit, which is really like physics, effectively. There's a fundamental limit to it. How fast it can process.
And this is where we initially started nerding out on like, what are, from the first principles, the limitations of blockchains.
Correct. So this is like where you'll start seeing the fundamental limitations of blockchains. Let's start off with just a simple machine model of a computer that has a network, and it has memory, and it has a processor. The very basics, not even storage, before we get into the storage part. So the bottlenecks here, the very first one is the network, the messaging bus. Typically speaking, not really. The messaging bus for Ethereum, for Bitcoin, for everything is very fast. Like internet is fast. It can propagate messages pretty fast, right?
And just to clarify, the messaging bus, do you mean like how fast?
The networking bus, like how fast it can send the messages and receive the messages in that channel. So
like once you submit a transaction to the network, how fast can that transaction get propagated to nodes?
Correct. Exactly right. How fast that can be. Awesome. Now, technically that could be a bottleneck, but you don't really see it being a bottleneck unless you're in like extremely high like streaming services like a Netflix or something like that, where they are streaming literally terabytes of data nonstop, like maybe every minute. I don't really know, petabytes every minute. I don't know. But these kinds of capacities are really required. You need like giant fiber optic networks to just blast this thing out globally. You're nowhere there. It's like for the most part, the network is really not a concern, like the hardware concern, rather. Then you have, so simple model. You have the networking. Now the message comes in. It is an instruction. Hey, Alice to Bob, send this money. And now it has to update that instruction. So what does it do? It runs it through the CPU. The CPU is a potential bottleneck. Typically speaking, most blockchains don't really do complicated work. They're not like doing ML learning or anything like that. I mean, machine learning. They're not doing AI or anything. So they're not doing super complicated stuff. They're doing pretty simple things. They just read a bunch of instructions. They update a bunch of state, and that's it. And the memory in this magical thing is unlimited, so we don't really care about it, right? So in this setup, the only bottleneck you really have is the CPU. It's like how fast can the CPU process these transactions, right?
And is the CPU the virtual machine or the execution environment?
Great. So it's now I'm talking about very, very basic virtual machine of like
I'm jumping ahead.
Alice and Bob. Exactly, like Alice and Bob. But so if we start augmenting the virtual machine and we start making it more complex, the virtual machine obviously starts very suddenly becoming a major bottleneck, because that virtual machine within the computer has to do a lot of state transitions. It has to do update accounts. It has to update state of different contracts on memory. And even if though in this hypothetical, Gedanken experiment, the machine is only in memory, it's a fancy machine, and it does not do anything on storage, it's still a concern because it has to do a lot of memory operations. Now, typically memory is very fast, so it's not an issue. But at the end of the day, this is the fastest thing you can possibly build from any kind of processing, like anything kind of database system, basically. That's what a blockchain is at the end of the day, is a database system. And this is literally how like NASDAQ built a system, right? Like they just scale up vertically because they take one rack, like a giant, absolute monster rack, and then they scale it up to 3 million TPS because they have built super low level code that is super optimized for the hardware they're building. Like they're gigabytes and gigabytes of memory. A lot of it runs in memory before it even goes into storage. So like they're very optimized, right?
Yeah.
And even then, you're at like 3 million TPS.
Okay.
You can't get better. Like you literally cannot get better.
And one caveat with that is it's all sequential.
It has to be sequential. It literally has to be, because we're operating on a sequential linear sequence of events.
Yep.
Like if I have a photo streaming service and somebody's accessing photos in this particular area for a particular client, and somebody else is accessing photos for a different client, they don't have to be on the same machine. They can be totally sequential. That's, for example, where sharding comes in. It's a great thing. But once you start building a system where you have to have sequentiality, the whole parallelization breaks down.
For sure.
And literally the only thing you can do is you are limited by the physical capacity of your hardware to take in ingest data from the network, CPU process it, memory access bus, eventually down to storage. But that's like your physical limitations.
So just for everybody else listening, we're touching upon from first principles the limitations. We started out with like data propagation for all nodes, and then went into the execution environments. The other two, or that we haven't touched, we kind of touched upon storage. But then the other one, I think we'll probably get into it, is the consensus algorithm.
Correct. So that's the algorithmic limitation. So we're talking about just physical limitations. Right now. We're not even talking about the mathematics behind it, because mathematics comes very deeply into play. And this is like what's something that like is so complex to get through to people, because the mathematic, we're building algorithms, and algorithms have they have mathematical limitations. Like they're built by humans and they have complexity rules to them. Complexity is like how many instructions per a unit of input in bits does the algorithm take? Is it linear, logarithmic, quadratic, exponential, all these things, right? So we haven't even gotten there yet. So we're talking about just a pure single machine that has like some sort of a virtual machine, let's say like the Ethereum virtual machine, and all of the limitations there is how fast can that memory and that CPU and that network just run through these instructions. Of course, there's also at the end of the day, the storage, but for the most part, you can actually ignore the storage because there's all kinds of pruning things you can do. You can disregard old state, and it comes down effectively to the memory and accesses. But you can't disregard a badly implemented database. A badly implemented database will absolutely screw you. Accesses, especially of old state, will get you to start hitting things that are very much not cached. And now you're starting to traverse down trees into storage of different files, and it's a mess. So badly implemented, you can get really screwed there. So in this super simple model of this very simple machinery, like we don't have a block, even if it is a blockchain, like as in like a sequence of blocks, it's a simple model. It's a single machine. There is no complexity here. The complexity starts coming in when you start going from just one machine to just two machines. Forget like 3 or 4 or n of them. So just two machines. Now you have complexity because the algorithms now are rulers of this new world as well. And when an algorithm is a ruler, there is complexity to the algorithm, as I just mentioned. So going from one machine to two machines has all kinds of implications. And it has implications depending on what your assumptions are. So now we get into the very subtle things. What do I mean by assumptions? Well, are these two machines now real machines? Like they go to storage and all that kind of stuff. They can communicate with each other. Are these two machines crash fault tolerant, meaning they can only shut down and nothing else? Or can they act maliciously? So that's one big consideration of it. And typically speaking, if you have things that are crash fault tolerant versus Byzantine fault tolerant, CFT versus BFT, things are much easier with the CFT world. Significantly easier, in fact. You can make all kinds of really easy assumptions about how you can reboot the system and all that kind of stuff. So the algorithms are much less complex and much easier. Like common things are like a two-phase commit, right? Like you don't have to use some complicated consensus algorithm, just two-phase commit. You have a leader, gets a message, gets two round trips, boom, done. Like it's simple.
Yeah, I do think a lot of people, or at least Web 2 people that I know, that have done like large scale production kind of distributed or database systems do kind of confuse the two. And they try to map that world to the blockchain world, and it doesn't work.
No, it doesn't. It's different assumptions, different environments. Like Chubby, which is the CFT replication service that Google uses, has been using it for decades now, maybe decades. It's a long time. It's so fast. It's a replica. You can have like 5 nodes and they're replicating data, and it's blazingly fast, but it's also crash fault tolerant. So once one of those starts acting maliciously, everything goes out the window. You can't use this. You can't assume any of the data is correct. It's a whole mess. So that's the first thing, is like, what kind of environment are we even in? So for the blockchain system, building resilient things in the open internet, you definitely want BFT. You don't want CFT. So throw CFT out the window immediately. The only thing that's left is BFT, Byzantine fault tolerant systems. Now, when you get to Byzantine fault tolerant systems, there is really 2 general network configurations. Well, 3, but let's ignore the third one because it's kind of subtle, and this is like where like distributed systems like literature comes to play. We're not going to get into the third one. So there's only 2, and and it has to do with how the network communicates with, how these 2 nodes communicate, or 3 nodes communicate with each other. Do they communicate with each other synchronously, meaning that like every message is assumed to arrive within a certain delta amount of time, or is it acting asynchronously, meaning that a message is sent and it will be received whenever, and it will do the next processing only when the message is received, right? This has deep implications because synchronous protocols have very different performance guarantee or performance properties than asynchronous ones. Synchronous ones are much slower than asynchronous ones. And you may say, why would I ever use a synchronous protocol if it's slower than an asynchronous protocol? Well, because they're easier to implement. Okay. And they also tend to give you some really nice other properties that we can get into a second. So, so let's go down the synchronous path first, because that's kind of like the V1. Like synchronous is simple, but it also has limitations. So synchronous model, you have 2 machines and they can communicate. They're guaranteed to communicate with each other within a certain period of time. That's the assumption. Bitcoin, well, specifically speaking, Nakamoto consensus is a synchronous consensus protocol. It assumes propagation of a certain amount of time. Now, when I say synchronous, I mean like it is safely synchronous. That means that it will guarantee that you will not double spend as long as the network remains within delta of time propagation.
And just for everybody else, and correct me if I'm wrong, the Nakamoto coefficient, or not coefficient, the Nakamoto consensus algorithm is just saying all nodes in the network have to download 100% of that information before propagating that information to another node.
It's actually slightly subtle. You have to have at least 50% of the nodes download it in Bitcoin within 10 minutes.
Okay.
That's the block time.
Gotcha.
Right? So that's why you have to wait 10 minutes, because it assumes that within only 10 minutes will 10%, 50% or more of the network take that.
I see. And I think Ethereum is also similar in regards.
Ethereum has much lower block sizes, but that's irrelevant because at the end of the day, what you're looking for is how much of the hash power has confirmed or voted on a particular block.
Gotcha.
At the end of the day, it comes down to to votes.
Yep.
It's just voting. That's what it is, right? But instead of voting by like a signature, like you would do with a voting-based protocol like proof of stake, which we'll get to, even though proof of stake is not a consensus protocol, but people recognize it as such. Instead of voting with that, you just vote with hash power. You just say, I vote on this block because this block I mined. That's it. Or if I didn't mine this block, I'm going to vote on the block that follows it and points to it because I mined that one. So it's just incremental votes on a particular path.
Gotcha.
Bitcoin only works synchronously. So if the synchronicity assumption breaks down, meaning that like 50% or more of the network does not receive the blocks within 10 minutes, or as Satoshi did it within an hour of the propagation, which could happen. For example, let's say there's a split in hash power between Europe and America. Like they don't communicate for 2 hours. There could be like an intercontinental divide of the internet, right? In that case, America continues operating, Europe continues operating completely independently, but they're totally unsafe because when they merge, one of them has to be overwritten. And it's the one with the minority hash power. And so all the blocks that got confirmed on the Europe side, let's say Europe is the minority one, then all the blocks on the Europe side will get completely wiped out. And they will get overwritten by the America side because America has more hash power in that case.
Gotcha.
Okay? So, but here's the key part, without getting into the complexities of it. And we can talk about complexities of how this arises for a voting-based protocol as well. But because it's synchronous, you make an assumption of necessarily, I can only download this much data for this delta time. I'm really bound to it.
Yeah.
Which means that I could have the world's fastest machines ready to ingest gigabytes of data, but I'm only saying I will only ingest 1 megabyte every 10 minutes or 2 megabytes every 10 minutes.
Gotcha.
That's the limitation. Why? There's decades of fighting because some people say that like we need that because like some small nodes, right, won't be able to download, gigabytes of data every minute or whatever, all that kind of stuff. But this is what it comes down to. Literally, it's an argument of the more data per second, the less likely it is for small machines to keep up. So now you have a tendency to only allow the big machinery to stay ahead.
Correct.
Of everything.
Yeah,
so that's
makes sense.
Yeah, that's the Bitcoin argument. And the Bitcoin block size wars. Debate. So
no, it is interesting. I don't know. Yeah. I think it's interesting just ultimately where we'll end up heading with like the different hardware. But I appreciate that these different communities and different blockchains are trying different avenues.
Yeah, that's fine. But at the end of the day, like whether Bitcoin Cash is right and Bitcoin is right, I don't know which one it is. That's what it comes down to, right? Like, is Bitcoin right in being 2 megabytes every 10 minutes? I mean, hardware has improved a lot. Probably not. Like, it could probably increase, but that's heresy in this environment. I can't even say that. So really, like, whatever it is. But then also, like, incrementing into like terabytes per minute, it's not possible as well. Like, it's true. Like, it will be very centralizing very quickly. So this is where like the bottlenecks are with a synchronous protocol. You literally have to like pick some arbitrary number, like how much data every minute can we possibly ingest as a network? How do you even pick that?
Yeah.
Like, it's completely arbitrary, right? Bitcoin it's 2 megabytes block size, right?
I think the blocks are 1 megabyte every 10 minutes.
Either 1 or 2 megabytes, whatever it is. Yeah. That's the parameter that got just chosen by the community, Satoshi initially. And I was like, this is it. Yeah. Like, there's no other sensible reason for it. But is 1 gigabyte better? Is 10 gigabytes better? Who knows? Right?
Yeah, no, I totally agree. And I think this is why, again, like, I appreciate these different trade-offs being explored within the different communities. Just because, I don't know, if it is arbitrary, then why not explore the different trade-offs and see what is possible?
True. But then again, you do have a lot of fragmentation, a lot of these things. So asynchronous protocols are more like art than science. They're just pick arbitrary parameters.
Yeah.
But in any case, getting to the bottleneck of Bitcoin, the bottleneck of Bitcoin right now, I'm talking about Bitcoin specifically, not generically Nakamoto, although we can talk about that, is the fact that it can only accept 1 or 2 megabytes every 10 minutes. It can't accept more. Even if you have extremely powerful machinery, it just will not accept more because it is beyond the rules of the synchronicity assumptions of Bitcoin.
Gotcha.
Ethereum is also the same exact thing. Ethereum, I am blanking out on the gas limit, but gas limit is like every minute or whatever it is, effectively dictates how much data we can ingest with Ethereum. Ethereum and Bitcoin are both Nakamoto right now, and that means that they are synchronous, which means that they have a arbitrarily chosen parameter, and that's the major bottleneck of Ethereum right now. It's not the storage thing. Storage can be a problem, but I assure you, storage is not a problem when you have such incredibly small like ingestion rates. With these nodes, it's still a big issue because the state is blowing up. And here's the other big thing with Ethereum and Bitcoin and Nakamoto specifically, is that you can't prune state. And the reason you can't prune state has to do with the way that Nakamoto operates. You have to have the longest chain, and you have to prove that you are on the longest chain, right? Like suppose that we suddenly prune Ethereum right now. Then you're automatically violating the very assumptions of safety of Ethereum, because you're saying socially, this is the new genesis of Ethereum. We can disregard everything else, but there is nothing else to it. It's just like a social consensus. So you've thrown out Nakamoto, and you have said, I don't care about everything else before that. Bitcoin, actually, I don't know if Bitcoin does this, but Ethereum for sure has done this. They have like pruned out all state past a block because the state grows too big, right? So they just have to like disregard it all and be like, all these blocks prior to this are gone, and literally you put the hash of like where you're starting in the GitHub, GitHub, and here it is. Download it and run it. So that's the bottleneck from a operational perspective for a synchronous protocol. So how does asynchronous protocol work? Asynchronous is completely different. Asynchronous doesn't care at all about what the parameter of speed is. It just says literally, as soon as I get some supermajority of votes for anything, I will process. I will work as fast as the network allows me to work at, right? And
by supermajority, just like whatever percentage of the nodes voting that like something is valid.
It's 2/3 at least, typically, all that kind of thing. Because there is like safety arguments for voting based. There is no asynchronous Nakamoto. There's only synchronous Nakamoto. It can only work synchronously. But there is voting based protocols where you literally vote signatures. Like a bunch of people and you vote, and that's how proof of stake works. And they work asynchronously. They can work asynchronously, but they have this limitation where you literally are bound by however fast the supermajority, the fastest supermajority of the network is. So if the fastest supermajority of the network is processing 1 gigabyte per minute, then that's as fast as this goes. So it's unbounded, right?
Gotcha.
It's only as fast as you can put machinery on it. But now there's a problem, because suppose that's great. Like we just process things as soon as the information comes, we just run it through. There is now a tendency, like the fastest thing you can do is just reduce that complexity from many machines to one machine. So we're back to now the processing speed of one machine. So the second that we add 2 machines or 3 machines and so on, voting-based protocols, asynchronous, they work asynchronously, have very large communication complexity. And this is now where the algorithmic complexity comes in. Communication complexity effectively means I can't just accept something and produce a block in the same way that I would do with Nakamoto I don't care what other people in the Nakamoto consensus think. I just get a transaction, I produce my block, and I push it out. I don't care. In a synchronous protocol, I get the transaction, I check whether it's valid or not. Now I have to ask everybody else, is everybody else okay with this? Now,
Gotcha.
I ask everybody else, is everybody else okay with this? They have to respond yes or no. So I collect these responses, and now I have to produce a large proof that I show to everybody else that says, here's what I see that everybody else votes on. This has cubic complexity. Mm-hmm. So O of n cubed. Basically, it means that so if you have 10 nodes, just 10 nodes, O of n cubed would be 1,000 messages, right?
The overhead gets very large very quick.
Correct. It gets very large very quick. So for example, I know you love Solana, and I like the Solana guys, but let's talk about Solana for a second. So Solana is...
I think we'll get there eventually.
Yeah.
We have a lot of things that we're going to talk about.
Yes.
Or maybe try to we've talked about the history, kind of talked about Bitcoin and Ethereum and their overhead, and now on synchronous versus asynchronous. Let's try to finish the asynchronous stuff.
Sure.
And then we can go to the different protocol comparisons.
At the end of the day, in asynchronous protocol bottleneck, it's not on the message propagation. It just goes as fast as the network. It is not on the storage. The storage is as fast as the storage can get. It's really as fast as your machinery can get. The problem is that when you start introducing more and more replicas,
more nodes,
exactly, in the network. So you have more decentralization,
uh-huh.
Which I'm quoting because decentralization tends to be very ill-defined. But suppose that you have equal stake amongst every node, and you add more and more nodes, and you spread it out uniformly. As you do that, in a perfectly decentralized network of thousands and thousands of nodes, each with equal stake, each with equal say, it becomes prohibitively expensive. In fact, the performance drops
because it is quadratic.
It's actually cubic.
Or cubic,
yes. So it's very complex. There is quadratic ways in optimal cases, but for the most part, in the worst case, when you have to do a view change, it becomes cubic and it becomes a big blowout. So it's very complex. So unlike when you had one node where you just get the message, process it, you now or 2 nodes or 3 nodes, which is pretty simple, small. Now, when you have 100 nodes, that gets massively complex. I have to collect all the signatures. I have to show these signatures, process it, push it out. So it becomes a big mess. And that's probably the biggest pain in the ass when you're building asynchronous protocols. Is partially why, for example, Cosmos has only 100 and something validators, because if you blow it up more than that, you run into a big problem.
The communication overhead.
Yeah.
Gotcha. Interesting. No, I mean, I love it. I think this is the level of granularity that is hard for people to digest, but kind of laying it out in the long form makes it much easier.
Yeah.
Awesome. We touched upon the history. We touched upon Bitcoin and Ethereum. Ultimately, what we're trying to do is establish a base ground from first principles of how these blockchains ultimately work. That being data propagation, the execution environment, consensus algorithm, and storage eventually. And we've kind of walked through the synchronous versus asynchronous and the different bottlenecks over each of those. So, and I guess that would kind of be the traps that you're kind of looking out for when building these distributed systems. What is the messaging overhead between them? And as you scale the number of nodes within the network, how large does that communication overhead become?
Exactly. That's a major issue. This is decades of research in distributed systems was literally, how do we get that message complexity down?
Yeah.
Because I can assure you, you take Cosmos and you run it with 2,000 nodes, the performance will just be atrocious. It cannot process those. And similar other proof of stake protocols, right? So if you take Solana, for example, as well, and it has 1,400 something validators or something like that right now. The thing with those, though, is that it has a very tailed distribution. So there's still only a small number of validators that actually account for the supermajority of of nodes.
Just because the number or the amount of stake assigned to each of those individual nodes.
Yes, exactly. And then there is a very large tail of those 1,400 that have almost zero. I don't think is there a minimum staking requirement for Solana? I don't think there is, right?
I don't want to say it incorrectly. I know to be profitable, you have to have a certain amount of stake.
But I'm saying like to just literally be a validator, you don't have to have any minimum.
You have to, for Solana specifically, you have to have some amount of Solana just to be able to vote for the transaction.
Sure.
But I think that's like the bare minimum.
Bare minimum. But that value can be super small.
It could be until you run out of Solana.
Sure. It's not like Avalanche where it's like 2,000 VOX per validator.
I think eventually, they'll implement slashing, and then you'll probably have to have like some amount of stake. But I could be wrong today that you don't have to have like a bare minimum. Okay. I think they idealistically like want people to have obviously be profitable in the nodes.
Sure, they want to increase that.
So if you're not making money, then there's not a large incentive to run the node.
But I do remember seeing the numbers on the distribution. I do remember seeing those with small amounts. So I assume like full validators. So I assume there's very little requirement, if at all. So in any case, the actual number of nodes, individual nodes that have to do voting in Solana that account for the super majority of votes is still pretty small. It's not much more gigantic in Avalanche, right? Like, let's just be very clear. But there's a critical but here, which is that if you were to create a hypothetical universe where you were to take all of the Solana stake and distribute it equally amongst 1,400 validators versus take all the Avalanche stake and distribute it equally amongst 1,400 validators, the key difference, and this is like where the algorithmic breakthrough with Avalanche is that Avalanche does not have that qubit complexity at all. So you could theoretically get to 1,400 or 10,000 validators with identical stake, like fully decentralized, fully distributed, and Avalanche would not care. Like, it would just operate at the same speed and everybody gets to be a full validator. It's not like a delegated proof of stake or something like that.
And ultimately, this is kind of why you can have so many different subnets doing different things, correct?
Yes, you can have a lot. You can have, we haven't tried it, but you can have hundreds of thousands of validators with equal stake, and each one of them is doing their own thing with different subnets. But at the end of the day, the big breakthrough algorithmically of Avalanche is that it is genuinely, not like, oh, it's fast and all these things, is genuinely a very distributed system, or rather, I should say, very, in a very intellectually honest way. It has the ability to be far more distributed than Bitcoin does. Now, is it today? No. It still needs work because it's still so much newer. It doesn't have the same amount of distribution that Bitcoin does, but it can. And it literally will never be a problem for Avalanche. It doesn't care how many nodes there are. In fact, like, we can just start throwing nodes left and right, as many as possible. Amazing. Like, we just get more decentralization, and the network performance will not suffer. And the key thing is the algorithmic part here, right? Like, that's where the big breakthrough came in, and it has to do with the probabilistic. We talked in Barcelona. It's the probabilistic nature of it. So all the work prior to Avalanche, all the distributed systems working in asynchronous protocols, it's deterministic. That means that once a certain threshold of nodes vote, you are guaranteed with probability 1 that the vote, assuming the number of Byzantine nodes does not surpass a certain percentage, blah, blah, blah. You're guaranteed that your transaction is safe. It will never be reverted, finality, all that stuff.
And 1 for the normal population is 100% confirmation.
Correct. Yes, 100% confirmation. So, like, it will never be reverted. Right? Avalanche, there is this. So it turns out, and we had the same exact conversation in Barcelona, and I want to repeat it. Because I think
it was a good conversation.
It's very, this particular part, because I think it's very interesting. There is something interesting that happens. There is this whole field called complexity theory in computer science, which is literally the study of how complex are algorithms. And I did I T8 courses on this thing. And one And so there's problems or algorithms in computer science. You have a CS degree, you know. There's problems in computer science that have very large complexity, like they're exponential. They're very hard to solve. NP-hard problems, they're called, right? And these problems, like once you start getting to like large input sizes, like the traveling salesman problem, for example, or the Hamiltonian cycles, once you start getting to large blowout of inputs, it's infeasible. You can't solve it in any like any reasonable, like thousands of years of processing until you get a solution.
Yeah.
But if you don't care about an exact solution, you can collapse. And this is like fascinating. There's like so much beautiful theory around this, but you can collapse the complexity of that algorithm down to something much, 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 much simpler, only because you said, I don't want 100% exact answer. I want 99.999% exact answer, type of thing. And turns out that when you introduce this possibility for error, just a tiny little bit of error, and it's not much, it's like exponentially small.
Yeah. What'd you say it was like 2 to negative 15?
It's very hard to say, but exactly right. Like we try to parameterize things based on like our own like upper bounds.
Yeah.
And I quote upper bounds because it's really hard to say. Like upper bounds are just very wide, right?
Yeah.
So we try to bound it with those kinds of parameters, but we don't know what the exact probability is. It's just very hard to compute. But yes, it's like
extremely
small. It's very small, right? And so in Avalanche, when you don't care about that, you just have a very tiny probability that you might indeed like make an error, then the complexity reduces. So you don't have this cubic or quadratic blowout in message complexity. In fact, it almost stays flat. Quote almost, because it's like small little thing there, but it's negligible.
Gotcha.
So now Avalanche can go to like basically 100 nodes, 1,000 nodes, 100,000 nodes, and theoretically at least it should have no performance. And we've done testing up to 2,000 nodes, and the performance 20 to like 2,000, no difference.
Okay.
It just, and all of them like equal weight.
Yeah.
So like fully distributed, just no difference, like basically the same thing.
Perfect. That's awesome. Yeah. No, I think, the small nuances are very hard to articulate on Twitter. So
it's very hard. Yes. It would have taken a very long amount of discussion too.
Lots of tweets back and forth.
Correct. I would have lost it completely and nobody would have seen it.
Yeah. So let me just try to summarize it real quick. We touched upon the asynchronous versus synchronous, why synchronous has some interesting properties, but properties that maybe don't allow it to scale very well.
Yeah.
And the asynchronous ultimately can scale more so, but there's whether it's deterministic or non-deterministic.
Yeah, it can scale depending on the number of nodes.
Okay.
Right, and if you use the deterministic properties of like a Tendermint Cosmos style thing, then it can't scale to many nodes. And if you give it some error, like Avalanche, then you can scale to many number of nodes.
So with a small, very, very small degree of probability of error, you reduce much of the overhead complexity that arises when you start to add nodes to the network in these distributed systems. And the additional nodes can kind of increase the overall censorship resistance.
Yeah, exactly.
Awesome.
At least in theory.
Yeah.
At least in theory, right? Like maybe, you end up centralizing because people don't want to run their own nodes or something like that. But at least in theory, Avalanche should never hit any bottlenecks as far as like algorithmically speaking.
And then we kind of touched briefly upon like the super minority of nodes.
Yeah.
And Avalanche is leading, and the super minority for everybody else is just the number of nodes that need to collude to kind of screw with the network.
Yeah.
Avalanche is number 1, I think, today. I think Solana is number 2, which is interesting. And then it kind of like trails off from there. But yeah, super interesting. So,
I mean, my goal is to just obviously incentivize as many people to run their own nodes with as much like distributed stake as possible. At that point, like you have little risk towards, well, not super little, but the risk should at least theoretically be minimized of like any attacks where like, a malicious adversary starts getting control of nodes. Like if there's just so many nodes and you have to corrupt so many nodes, like the probability of this happening goes exponentially small. So that's at least the goal.
That makes total sense.
Yeah.
So from your point of view, from like the first principles type thinking where we articulated data propagation, the execution environment, consensus algorithm, and then ultimately storage, the consensus algorithm is the biggest bottleneck to solve because that unlocks the number of nodes to scale and increase
for security. For security, right? Like if you don't care, you just want like 50 nodes or like 10 nodes, honestly, just use like something else. Like use like a Paxos implementation or something like that, and it's probably even faster or something like that. But if you do want to build genuinely like a very high performant yet, can scale to like thousands of nodes, I don't know of any other protocol besides Avalanche, right?
Yeah.
But of course, there's still things that need to be worked out, right? Like there's still bottlenecks now. So we've solved on the algorithmic thing, assuming, we have thousands of nodes. We don't have that bottleneck. Network is also not a bottleneck. The propagation is very fast. So algorithmically, no bottleneck. The network is not a bottleneck as well. The CPU is also not a bottleneck. So what is the bottleneck? It tends to be towards the data structure implementation. So like the EVM and memory and like storage access. That's what it comes down to at the end of the day.
So do we want to touch upon virtual machines?
Yes, we want to touch upon virtual machines.
I like talking about the virtual machines. I think why I got very interested, I personally like vertical scaling before you have to scale horizontally. I just like the different aspects that you get with the vertical scaling and composability. But what interests me a lot with Avalanche is that the node requirements are not prescriptive and that each subnet has the ability to have its own virtual machine.
That's right.
Which I found super fascinating because if you can actually customize the virtual machine, there's a lot of possibilities that you can do.
Correct.
Then I think I was talking with Patrick. He was saying you can even get down to the granularity of like writing the instruction set. Which I was like kind of mind blown because at Tesla, I remember on like the machine learning day for how they're training the cars for the neural network in their chips, they're going all the way down to the instruction set to simplify it as much as possible to make it as efficient as possible. So maybe we can start going a little bit into like the execution environment and virtual machines.
So that's, I think, the next frontier, right? Like we had all the algorithmic work up to now, and I think Avalanche solved most of that algorithmic work. But at the end of the day now, it's kind of like, let's optimize these other implementation things, not algorithmic things. There's no more algorithmic things here. It's just like implementation. It's kind of like if we had done it the other way around, of like optimizing the virtual machine, it's like building a supercharged engine, but you don't have a car. Like you haven't built infrastructure yet for it. Like you don't have the basics of it. So now we have to. The next frontier has to be how do we get the C chain, for example, to be extremely performant. Even when you have like an insane amount of transactions, because you want to be very careful with state growth and you want to make sure that every one of those transactions gets through a virtual machine that is fast and it's not like cumbersome and all that kind of stuff. So the EVM is, well, specifically speaking, the Golang EVM, like the one that's written in Geth, which is we take that individual part, the virtual machine from Geth, we call it core ETH, put it into Avalanche, and it just does the execution. So that part is fine, but it is far from like a high performant virtual machine, right? Like Wasm is so much stronger. And Solana uses Wasm, others use it, like it's just so much stronger. But also nobody develops yet in that virtual machine. It's, they're trying to change it, all that kind of stuff, but it's complex. We understand solidity. So like from a go-to-market, like we're not virtual machine builders. Like we're gonna get to that point, but we're algorithmic people. We're people that build distributed systems, and so we were like, look, just get the best, the most popular virtual machine right now, which is the Ethereum virtual machine. It's kind of like building a new browser. You don't want to like implement like a different scripting language that every website has to implement, right? Like you want to just get HTML, CSS, JavaScript, run it. You get the V8 engine, boom, done. So same thing here. We just implemented the EVM, but it has a lot of issues. And In fact, like the way that it does the instruction, it's just very suboptimal in a lot of ways. And there's so many ways that you can optimize that. So without even talking about storage, so you can talk about, can we get like just-in-time compilation? So bare metal running, like that's an important new optimization. It's a little bit complex, but that's amazing. So rather than interpreting every instruction like the Ethereum virtual machine does, you now just pre-compile it, boom, into bare metal, and now you run it. That's a huge gain, and we're doing work internally on that. We're prioritizing different optimizations, but that's a very big one, like the Java.
So could you do that to every individual subnet, or would that be its own individual subnet?
Yeah, if we roll out this new EVM++, then you can just take it, implement it in the C chain, augment it. The C chain now supports the EVM, let's say EVM++. Now you can do just-in-time compilation.
Okay.
That means that every contract invocation, everything is pre-compiled, which is just blazingly fast. Or you can just put it onto only specific subnets and use them there only. Or you can use entirely different execution environment as long as it understands Solidity, as long as you can compile everything down to the same bytecode that Ethereum builds, and you can use those compilers. Then all this work can be done. So optimizing accesses at the virtual machine, that's a huge one, right? Like Ethereum has so much Merkle stuff beyond belief that now we have to deal with it. And it's not something that we can easily gut out because it breaks down things. And so now we have to carefully and surgically take this thing and start removing all these things one by one. But at the end of the day, these are just a matter of engineering and implementation. There's no algorithmic work here. It's just literally take the usual things that we know for building fast virtual machines, and there is so much literature, and just implement it. And it's inevitable. Like within this year, the goal is we push out kind of like an EVM++. It's going to take a little bit longer, probably towards the end of the year, maybe next year. I don't exactly know where. But in the meantime, push out the other optimizations which are important to fast sync. So we want everybody to start syncing up to the network really quickly after you start a node. And then pruning. So all this contract state, so much of it can be pruned away, right? There's so much contract state that you can get rid of because a lot of the contract state is inert, completely inert. So you can just throw it out. You can throw out all the previous blocks. The database can reduce down in complexity significantly. And really all you have to take care of is managing the active state, like contracts that are active and have active accesses, and optimize the crap out of them in terms of caching. Yeah. So you have a contract, this contract is very, very used. Start putting it in memory basically, and start leaving it there so that whenever a new invocation comes in to update that contract, I'm not doing a single check on storage. I will never hit storage, in fact. These are all things that are just implementation wise. You just have to make sure you don't screw them up. But this is the kind of things that will take to the next frontier of development.
That totally makes sense. Yeah, it's interesting on the execution environment within the virtual machines, just how much optimizations and really just how prescriptive. I mean, with Ethereum specifically, just being the first kind of smart contract programming or smart contract or Turing complete blockchain, we've all kind of been forced into the EVM. But when you can create a different execution environment and different virtual machines and optimize that, and with a good amount of speed, it's interesting what the future builders will be able to build.
Yeah, exactly. It's the people that might work in Python or have been working in Python for a very long time. They know that Python did not have Cython initially. They the very first iterations of Python, atrociously slow. Python was great only because it was a very clean, beautiful language to work with. Yeah. But Python today is just absolute beast. It processes things fast, and it's still interpreted. It does a bunch of optimization in the backend, but it's still interpreted, and it's an absolute beast. So it's probably what's going to be the development of the EVM over the next 5 years. It's just going to be similar, right? You're going to have the EVM++ is going to provide all these optimizations. It's going to start pruning out all states. It's going to start doing just-in-time compilation and all kinds of caching and everything, just optimize so much down to bare metal that like people literally will be able to just like, I mean, theoretically at least, you should be bound by as fast as the CPU can just do signature signing. Like that's as fast as you can get. Like no faster than that.
Yeah.
And at that point, you can probably also parallelize it with GPUs and start sending them out back there, get some signatures. At that point, you can't do anything faster.
Yeah.
You literally are like just micro optimizations.
Yeah.
And I don't know what that number looks like, but I would not be shocked if we're like at 10,000 transactions per second at that point. That's years and years away. But getting to that level with good pruning, good state management is absolutely imminently doable. Even on like low hardware stuff is what I'm talking about.
I see. So you think it's going to be super hard to get over 10,000 TPS?
Just because there's like literally limitations to like how fast I can do ECBSAs on a Intel CPU. Like the Intel i7, I think is like 9,000 single like per second. ECBSA signatures. And like I don't think you can get any faster than that unless you use a GPU. But then again, like you're bound by memory access. Like I would be shocked if you get any higher than that. Frankly.
Yeah, I'm super interested just to see over the long term how far we can push it and all the small optimizations and how they add up. But
I mean, a good upper bound is like NASDAQ. NASDAQ is like 3 million TPS.
Yeah,
you can't get any faster than that on a single sequential thing, unless, and this would be like a very interesting thing, is if we somehow change the C chain model or like the Ethereum model to be a parallel blockchain, like a blockchain where
parallel processing,
like where like smart contracts are invocated somehow in parallel, but the complexity around that it's absolutely insane. In my opinion, not worth it because there are so many other optimizations that are going to get us to a point where we're not going to need it.
I see.
Like we're just not going to need it.
So you're much more of a fan of trying to optimize the hell out of serialization before going the parallelization route.
Yeah, because I think if you go down the parallelization route, there is a non-trivial probability you're going to hit fundamental limitations to scaling. You're literally going to get slower, weirdly enough, because every time you do like these cross contracts that have to communicate with each other and they're on different parallel tracks, everybody else slows down. Amazing only like as long as these contracts are doing nothing with each other.
Yeah.
And it's amazing. Then I can have like, it's kind of like if I have a file storage system, like or a Google Photos clouds, like independent users can have their own independent shards.
Yeah.
But the second that I start having intercommunication with them, everything breaks down. And like the performance might actually be worse, literally worse, and not might, guaranteed worse than a linear sequential operation.
The tree of complexity of contracts that overwrite to each other and trying to parallels that does get pretty deep pretty fast.
It's very deep, very fast. Yeah. Even in like a baseline new ecosystem, let alone something sophisticated like Ethereum or Avalanche. Like it's just, I mean, you would require 20 years of work to get this thing done right properly. So sequential is the only thing that like makes sense even remotely.
Okay.
And but then again, like you still have places like, you know, where, well, so we recognize that the C chain still, until the EVM is improved, until the storage is improved, there's still fundamental limits to it, right? So we don't want to get, like we've capped the gas limit because we don't want the storage to blow up too much. Once the storage gets much better, the gas limit can start going way up and you can start seeing hundreds, if not thousands of TPS on the C chain alone. But until that happens, it's literally artificially capped with super high gas fees. So you can put a pump and a brake on the network because there's like machines that are running on the most absolute minimal settings on AWS or like cloud computing for Avalanche, like full nodes that have the worst specs I've ever seen. And the second that we start incrementing the gas limit, those nodes are out of sync. Right?
And if you do increase the gas limit, it's ultimately from like the pruning standpoint or from the standpoint of you need low node requirements. No,
it's not. It's just fundamentally it comes down to just like how fast we can like basically if a node right now on Avalanche goes out of sync, it is 100% because it is unable to respond to queries fast enough because it's literally backlogged on processing its own state because it has so little hardware power that it literally cannot process things.
So because the node requirements or that specific instance does not have enough compute or RAM or whatever it needs it can't keep up.
And it can't keep up because it can't respond and it can't download new things.
Gotcha.
So now it's like self-forking itself, right? Like
gotcha.
It's just,
So theoretically, like you could increase, the gas state today, but you'd have to just increase the node requirements.
Correct. It would have to increase.
Gotcha.
Same as like Solana does it. So you would have to go much higher.
Very interesting.
Yeah.
No, it's we've touched upon a lot. The difference between asynchronous and synchronous, the first principles of consensus, the execution environments, and data propagation, maybe, and then also storage. I think it would be interesting if we kind of touched upon a little bit more of like, how would you personally describe like a subnet?
Yeah.
Because I think it's a novel concept that people are still trying to wrap their heads around.
Yeah.
Like what is a subnet versus like an individual blockchain? Is it a subnet like its own blockchain? Like in your words, how would you kind of describe a subnet?
Yeah, there was a really good tweet by Corey Petty recently, and I'm totally blanking out on exactly how it went, but it was something along the lines of a subnet is a subset of the Avalanche validators that agree to process data in some way. Like generic, like super generic.
Yeah.
It can be anything, right? And that's really powerful because now I can just borrow a bunch of the validators from Avalanche, and then I can tell them, hey, run this other virtual machine that I'm going to give you, or run this other requirements for me, right? Like I want you guys to have a certain amount of requirements or whatever it is. And a subnet is effectively it's effectively the long-term future scaling answer to like, even when C-chain gets thousands of transactions per second and all that kind of stuff, like with low hardware requirements, even at that point, you still are not going to be able to subsume all the world's demand for compute. There's going to be always different things, always different games are super intensive, right? Like all these things. So subnets are a way to effectively externalize some of these independent requirements that certain dApps have, and put them on a different shard, if you want to call it, or a different a subset of validators who only them and them only are responsible for managing the state. So it's a very generic construct, but it's a very powerful construct because now, unlike, I'm not even going to talk about Polkadot's parachain because it's like irrelevant to me. But Cosmos zones are actually really cool. But Cosmos zones also have all kinds of requirements over what a zone is and so on. A subnet doesn't have any of these things. It's just borrow a bunch of validators from the primary network, a subset of them, and they become your new machinery for running a new blockchain.
Interesting.
So
if you borrow from, say, the main Avalanche validators for a subnet, what are the pros and cons of that in your mind? And then also that subnet can have its own validators, correct?
It just borrows validators from the main network.
Could you spin up like your own validators for like an individual subnet that don't need to be validated by the main?
No, you have to be part of the main.
Okay.
And so now we get into generically not blockchain design, but good engineering design, just generally speaking. And there's a lot of different groups within crypto that claim that like having a subnet is not as secure as if you were to build an L2 or whatever it is. First of all, literally like a subnet can be an L2, because what I said is like a subnet is just any subset of one or more validators that run some virtual machine that you want it to run. And it could be the Starkware virtual machine. It can be whatever else you want, right?
Gotcha.
So a subnet is a generic construction. But generally speaking, from an engineering perspective, you don't want to create any claims over which network is the more secure one, because you can't really quantify that. The only thing you can say is there is some floor of security to any particular blockchain, which is like bound to some amount of like a Vox stake. And that's it. Like you can just really claim the floor. Or like this subnet has this much amount of a Vox stake behind it. This is how much like guarantees you can get from this. But you can't say anything else on security, which is like, because mathematically, like how do you define security in this case? Like you have assumptions.
Yeah.
Right? Like you have assumptions over like which networks have how many Byzantine nodes, and that's all you have. You can't quantify. Like when people are like, oh, Ethereum is secure, and so you build an L2. What if the L2 is more secure than Ethereum?
The best thing that I've personally seen written on this was like by Balaji on the Nakamoto coefficient, and but also, I mean, it does call out the like super minority to like be able to mess with the network among other factors.
Yeah, it's just very hard mathematically to quantify what security is at all here. So the only thing you can say is, what is your assumption for Byzantine nodes? Mm-hmm. Does that number of Byzantine nodes exceed the threshold that we require to be safe? If it exceeds that threshold, the system is broken. Ethereum is broken. Bitcoin is broken. Avalanche is broken. Period. If it doesn't, then there is no reason to doubt why one L1 is more secure than the other L1, which is like the point that it just does not get across somehow. The saying that Avalanche is less secure than Ethereum makes no sense, because they're both just basic assumptions of they don't have more Byzantine nodes than the threshold required, period. As long as those assumptions hold, both of them are safe. So the same thing, though, can be said about a subnet. A subnet, you can just assume that some majority, like the super majority of them are correct and they're doing the correct thing. But if you don't assume that, then why are you assuming that the Avalanche one, the primary network, is secure? So I never understood this like dichotomy of like, oh, no, Ethereum is secure assumption, but other chains are not, or Avalanche primary network is secure, but the subnets are not. It's completely up to the subnet to define its own security. Yeah. It's completely up to it. And it's based on the assumptions.
And that's one of the things that I've honestly appreciated, because if you're going to get down to like, all right, you can actually customize the execution environment with the virtual machines, why not make it as flexible as possible with like the security as well, and let individuals decide how much security
it literally is. It's like goes back to the principles of asynchronicity. Like you can't make assumptions about the network. You can't make assumptions about the Byzantine behavior. You cannot make assumptions about anything here. Literally, like you cannot, because otherwise you are single-handedly making some parameters that you scientifically cannot back them up. You're pulling them purely in an artistic way. There is no science behind it. And so once you go down the path of choosing that like something is secure versus something is not secure, you go down a path of complete subjectivity in this case. Yeah. So to us, it's like good engineering design must necessarily be the one where you give full flexibility to people. Both developers, they can develop whatever they want, and then the users, they use these systems. Right? So if somebody's using a subnet and it has only a small amount of a Vox backing it, don't use it if you think that it's too insecure. Mm-hmm. But it does not make an L2 any more secure whatsoever. Like it really doesn't. Like this like the economy is crazy. And I can go into L2s. We can go a whole episode on L2s and physiques versus optimistic rollups and all these kind of things. We could
talk for a while about a lot of things.
Yeah, about a lot of things. But like so to me, I want to avoid making subjective claims as much as possible. All right. So like to us, it's like we just build systems and then let the natural, lets the market decide what it believes to be secure and what it doesn't at the end of the day.
Yeah, and I think we largely agree on a lot of this just because of the engineering background, and it's hard to measure the subjectivity. And if you can actually measure something from an engineering point, then you can like most likely make progress on that front.
That's right. That's right.
The hard part is because there is a lot of subjectivity. It's a lot of nuance and haymakers back on Twitter.
Correct. It's I don't want to be in the business of ever making like subjective claims over security of anything, because I cannot do that.
Yeah.
I can only make assumptions about whether or not a network, a consensus protocol, like fulfills those assumptions of Byzantine tolerance. If it does, it's secure. If it doesn't, then don't use it. It's not secure. Everything is broken. So, but generally speaking, we assume these to be correct. We assume that Ethereum is majority correct. We assume Avalanche is majority correct, and they just work. The same thing can go down to a subnet, and it's without shared security. Now, you can still share security with the primary subnet, the primary network, although that has issues with, it's still a contract issue. And in fact, Tarun just released a paper, I think. He wasn't the author, but he retweeted a paper.
From Gauntlet?
No, from Trail of Bits, I think.
Okay.
Where they found major vulnerabilities in L2 implementations.
Okay.
Like they're broken. Or I don't know if they're broken, but it was a major vulnerability. But it's an implementation, not a theoretical one. Like theoretically, they're sound. ZKs are sound. But implementation-wise, literally, it's a smart contract that has to check on. Somebody has to provide the proofs of the validity checks and all these kinds of things. That smart contract has to read all that logic and process it appropriately. At the end of the day, it can be broken. It can be implemented wrong and all that kind of stuff. So in the same way, the subnet can also be just as secure or just as insecure. It's just a matter of assumptions. And I can't possibly get in the business of making assumptions here. So that's why, to me, subnet architecture, where you get to develop whatever you want without forcing or making claims about what is secure and what isn't, is the absolute cleanest, best design for building sort of a giant ecosystem of chains, all talking smoothly. I can't get in the business of making any assumptions here. So just do whatever you want.
I appreciate that a lot. I think if you're going to design a protocol, designing it for maximum flexibility and putting ultimately it into the engineering hands and let them kind of decide what they want to build is brilliant.
And I think genuinely engineers tend to move towards things that are of less complexity. I agree. And that's great. Of course, if there is total possibility that a subnet can have a lot of value tied to it, even though it has very small amount of a Vox stake, in which case that is problematic, right? But that is a market function. That is not an engineering function. That is a function of the market having to be educated that maybe you shouldn't have all this money on a subnet being run by 2 validators that have 2,000 Vox each. Maybe running on a bigger, more distributed one, a more sophisticated one. But if you're just doing some game tokens or something that you don't really care too much about, then it's perfectly sensible. And anything with shared security adds so much incredible complexity and downturns performance-wise. It's just not worth it at all.
Gotcha. Yeah. That makes sense. Maybe, yeah, so we've touched on a lot. The consensus algorithms, the first principles, touched upon subnets. Maybe, I don't know, be interesting if we touch on maybe some of the more slightly controversial topics with L2s and I know your favorite data availability.
Oh boy.
But unlike with L2 specifically, and I would like to kind of hear your take. I kind of think of them on a high level as data compression. And you're compressing data to use that block space on the L1 as efficiently as possible because the block space is the scarce resource. And you can do that in different flavors with optimistic or ZK rollups. But at the end of the day, it's just trying to optimize how well you can use the block space because at the end of the day, that's what you're paying for. But I'd be curious to hear kind of you touched upon it with subnets being potentially or can being L2s in their own right. But how, in your words, do you view layer 2s more holistically?
Yeah. Layer 2s come down to theoretically nice in a lot of ways, but practically not, or maybe you should be aware of pitfalls, right? So you're totally right. It's effectively data compression in a lot of ways. But data compression at the cost of what, right? So all these latency and sequencers being single machines, and you have risks in the contract implementation. You have so much. The question is this kind of, especially like you also need somebody to be checking the proofs and making sure that like
for optimistic rollups, and if the ZK chain goes down, somebody has to put the stuff back in there. So you're going to have to also have somebody to put that stuff there, right? So not even checking proofs, but just literally putting things back on the chain. Why do this? Why not just literally have a subnet that runs kind of like another chain, and periodically you start checkpointing in things to the main chain if that is an important thing to you? At the end of the day, that's what it comes down to, because here is where the mathematical thing breaks down. If you have a distributed system is a database replicated by a bunch of different nodes. If you're breaking down the assumptions of how this data was generated, it doesn't really matter whether you can go back to another chain somehow and like checkpoint back, because ultimately the data got corrupted completely. So if like a ZK thing, like let's say is running, and you have a UI, you're interacting with it, and you're a user, you're not really checking anything in the background, and it becomes corrupted. You have no ability to know until it goes back on chain. That corruption has happened. You have lost the money potentially. The atrocious things have already happened. You are down to the same exact thing you would get if you had built it as a subnet with like a bunch of nodes. They can do the same exact thing. So your main point is like, I mean, and I think this is true, the L2s are like their own individual blockchain.
Exactly. Until
you submit it back to the L1.
Submit it back to the L1. Yeah. But in the meantime, everything can go wrong.
Yeah.
In the same way that like if a corrupted subnet like has, 10, 20 nodes, majority gets corrupted and they want to do things, so you wouldn't know either. And you would also have no remedy. But what is good is a remedy when you've literally been corrupted in the data. Like there is no way, like you require more social engineering at that point than you require anything else. You have to get people basically to start figuring out a way to fix this. The algorithm is not going to fix this. So to me, like it's a great theoretical exercise with very poor practical implementations of it, and also practical considerations of what happens if things go wrong, right? It's great in theory, but in practice, like you are adding so much complexity for what you would still end up getting even if you just use the regular subnet that does not share the security. So I like it, ZKs. I have a background in cryptography. I like these kinds of things. ZKs are a little overkill in my opinion, but they're fine. It's just that at the end of the day, from a security perspective, and again, we're making purely subjective claims here because it's so hard to mathematically say what security is. But from a subjective perspective, I am making nothing but a claim that cleanliness and just almost like common sense wise, it doesn't seem like an L2 or a subnet with shared security is necessarily more secure than a subnet with no shared security. Which is kind of crazy, right? Because it has the word shared security in it.
Yeah.
But it's crazy that I'm making the claim that they don't have practical differences from a security perspective. So I think this is going to be a contentious topic of discussion for like a long time.
Yeah.
People are going to be like, no, I think that it's still, there is benefit to somehow moving the state back on it. We haven't seen this in action. We've seen nothing but state corruptions that have happened with L2s and all these kinds of things. They go down all the time. At the end of the day, it seems to me like we're not getting any benefit out of him, at least yet, right?
Yeah. I agree. I am interested to see how they work out long term. I think it's just kind of, as I said in the beginning, it's interesting just exploring all the different design trade-offs.
Absolutely. And
scale blockchains.
And people troll on me on Twitter that think that like I'm a hater of L2s. No, man, like I'm not at all. I think they're genuinely interesting.
Yeah.
They are very intellectually stimulating things. They're really, really cool to work on. I have a background in cryptography. I like them. They can also even, of course, work on Avalanche. You can have Starkware on Avalanche. We're hopefully going to collaborate with them. All these things are easily workable in Avalanche. I have no problem with it. I'm just purely talking from an elegance perspective.
Yeah.
Literally like option A versus option B. And there is a lot, like we can sit down here and talk about the ABC conjecture. Like no one cares about that, right? Like it's just of no practical consideration. It's intellectually curious to me, but it's of no practical consideration to most people. Same kind of thing. Like I don't view the shared security subnets as like a thing that seem elegant engineering design, because at the end of the day, you get the same result. I'm making the claim that you get the same result whether or not you share security or you don't.
Yeah.
If it's corrupted and the assumptions are broken down, mathematically you are screwed. Socially, maybe not, but mathematically you are screwed. You have to figure out a way to get out of this socially effectively.
That makes sense. At Tesla, one of Elon's kind of like driving principles: do not optimize for something that should not exist, and make it as simplistic as possible and delete as many parts as you can.
I think this is something that as a space we have to learn. I've been saying this in different threads, like we have to keep it simple. Like it's so important.
Simple
because
wins.
It really does. And like I think the long gone are the days of ideological pontifications about like how to build like what it means to secure. I'll tell you what it means. You build distributed, replicated databases where the number of nodes should not affect the performance. And at the end of the day, just get as many micro optimizations into the database system itself as possible. That's what it comes down to. And then make a generic development, use the common language that everybody speaks, which in this case is Solidity. And you got yourself like a winning combination for like building proper, beautiful systems.
Yeah, no, I'm super excited. I'm just having a product background, super nerdy on like the analytics side, and just seeing how many actual users use blockchains. It's not very many compared to the amount of dollars or hundreds of billions of dollars in these systems. And so I'm very, very excited for these blockchains to scale to actually get tens and hundreds of million people ultimately on chain and eventually billions, because this tech is so cool.
It is.
And once in the power of the majority of people, I think that's where we actually start seeing really interesting applications start to flourish.
But I think we should obfuscate the tech as much as possible.
I agree.
Completely.
I agree.
Like people, it shouldn't even seem like anything. It should just be like, I am playing this game on a subnet and suddenly I move it to the C chain. It just moves like sending like email, right? Like from here to here, from website to website, right?
Yep. Not very many people know IP addresses, but they know how to type in apple.com.
Correct. I would love to get to the point where literally like instead of having a single server behind a domain, you have a replicated service like a blockchain, but otherwise it's like foobar.com and boofar.com and all that kind of stuff, right? So it's just like that would be like the most beautiful thing. I can move value from one domain to the other seamlessly. And I don't even think about how this thing is working in the back end. It just, NFTs are moving. Tokens are moving. It's just seamless. Like that's the most beautiful thing.
No, I agree. I'm excited for us to get to that point.
But I think we're getting there. I think we're moving away from the ideological stuff and we're moving towards more practical things right now. So, but I'm still going to keep being told by somebody on Twitter how the next 5 years are going to look because of some ideological thing. I'm just okay.
Yeah. No, I agree. Cool. We've been chatting for an hour and a half. I think we have a little bit more time before some of my gear battery starts to shut off. But maybe, potentially if we want to do part 2 at some point in time, or we could also cut it. But we've touched upon a lot. I know one thing that you get trolled about a lot also is the data availability stuff.
Yes.
I don't know if you want to talk about that. We don't have to. If you want to go into that, or we can kind of move on and talk about maybe some other things as well.
Right. So I'll talk very briefly on it. It's exactly what the Elon thinks. You said it's like
simplicity.
Simplicity, right? Like you have to. At no point in this conversation when we're talking about what the assumptions and what how we build like a mathematical model around a blockchain system, never did we have to somehow require a module which tells us that the data is available, right? It's just not a module that is relevant to building a distributed system. It's like literally an orthogonal thing. Mm-hmm. You can add data availability. Data availability is effectively the module that says that I can make sure a certain data is available, right? Like I can download certain data. It is there for you.
And maybe even on a higher level for most people, it's just how much bandwidth each node has in the network. So how fast you can propagate data between nodes.
Yeah, that's part of it, of the module as well. But all of these things when you're building, I mean, specifically this module, when you're building and thinking about how to build fast distributed systems, it is not a relevant topic of discussion because it is subsumed by the critical assumption that we're making, which is that there is a supermajority of correct nodes. Mm-hmm. And when you assume there's a supermajority of correct nodes, you assume the data is available. And here's the critical thing. If you don't assume that there is a supermajority of correct nodes, everything breaks down. And then data availability and anything else cannot save you. You have broken down the very assumptions that make it possible for us to build distributed systems in a Byzantine fault-tolerant way.
So going back to the first principles, it's kind of like solving for one leg without solving for the others, which are like the execution environment and consensus algorithm.
Almost, I would probably even say that like it's solving for a universe which doesn't exist because we already made the assumption that it doesn't exist. And if with that a universe does exist, then we are unable to solve the problems that we have in that universe.
Okay.
It breaks down.
Yeah.
Right. So it's like I can't have an analogy right now that is simple to understand, but like literally that's what it comes down to. It's like there's a universe where I can guarantee these things, but like we've broken down the assumptions. If I assume that the nodes are correct, I'm guaranteed the data delivery. That's literally what the assumption is. The nodes are correct. If that is not the assumption, and the nodes in Bitcoin and Ethereum cannot deliver the data to me, then we have bigger problems at hand. We have data corruption completely at hand right now.
Gotcha. Makes sense.
Yeah.
Cool. No, thank you for touching upon it. Yeah. No, we've covered a lot. About an hour and 30 minutes. I guess, is there anything that we didn't touch upon specifically that you would like to articulate?
Yeah, I had a list of things from from the Twitter poll that I made. I forgot to check the list recently.
I wrote them down. The first one was, what is a blockchain? What are the bottlenecks? Which I think we touched upon. What are the traps? How should we structure communications architectures?
Yeah, as part of what I was talking about with like subnets and like how not to fall into traps where you're trying to force some data into one of the other blockchains for no reason, basically. Mm-hmm. Keep things independent, keep things clean with each other.
We touched upon L2s and shared security. We could go more into like Solana, ETH, and Avalanche and Cosmos, but I think we did a pretty good job of kind of touching upon
That's right.
The different consensus algorithms within each of those. We've touched upon storage and networking, the physical limitations of scaling, farming distributed systems mathematically, and
framing,
interpretations of assumptions.
Yeah, I think we've covered pretty much all of this stuff.
We talked about subnets and borrowed securities.
Yeah,
no, we've hit a lot.
Yeah, there's a bunch of other comments that people were asking me, but I'm totally blanking out on them. But I'm sure there's a part 2 at some point that we can do on all this stuff.
We definitely can do it.
I know that like for sure once I start giving when people hear the heretic comments on shared security that I just made, they're gonna start trolling me so much on Twitter. But again, to all the listeners, I don't hate L2s at all. I'm just like telling you what
from an engineering
perspective, like there's cleaner things, right?
Yeah.
Like, you can do better, slightly better. So in any case, I'm sure they'll have comments, but I think for this iteration, I think we've covered quite a bit of ground.
No, you did. It was excellent. One thing also briefly, you have a fire Twitter game. How'd you get good at Twitter? I'm over here like trying to tweet stuff, and then like I try to tweet some alpha, and then nothing happens. But apparently, give me the wisdom.
I think Dan Robinson maybe made this tweet. Somebody made it, but it was absolutely on point, which was like from 0 to 10,000 followers. You want to post like very high signal alpha, right?
Okay.
Like until you slow grind up, right?
Okay.
So you're, and then from like 10,000 to 50,000, you're mostly shit posting.
Okay.
And then 50,000 to like 500,000, absolute shit posting.
So above 10,000, just start shit posting.
Yeah,
hard.
start incrementing it slightly. At 50,000, you take it to the next level, and then I think at 500,000, Dan Robertson said like from 500,000 to 2 million, you go quiet. And you become a philosopher. You go quiet and
go the Naval route.
Naval route, yeah. And then after 2 million, you go back to Elon Musk and start shit posting.
Be the master of the memes.
So I think you just have to, you just have to have a sense of humor about it and just make memes whenever they're funny. But I do need to balance the shit posting a little bit more because I'm just kind of going at it. But I do want to introduce a lot of alpha and engineering stuff, but I think the market has changed. I think the market is, frankly, less interested because there's been like years and years of discussion on this and people learning. And now I think it's just a matter of doing the boring but very important thing of like, let's just make these things seamless.
Yeah.
And that's super boring, by the way. Like it's going to get to the point where these systems, like Avalanche, is going to get to the point where like you just don't even think about it. Like, do you go and rave about how good Firefox and Chrome is? No, you don't care.
You use it.
You just use it.
Yeah.
And that's the point that Avalanche is probably going to get to, where like you're just using it and nobody ever even talks about Avalanche anymore at that point. And that's an amazing place to be in.
I fully agree. And getting back to like abstract all the complexity of whatever blockchain you're using and you just get the benefits of that.
So this is now engineering work, and engineering work is boring. Like it's just kind of boring, right? Like monotonous. It's not exciting. It's not like intellectually stimulating and talking about the cool ZKs and all these kinds of things and cool stuff with cryptography and homomorphic encryption. But I'm sure somebody will come up with something cool. So I think the intellectually stimulating part of the crypto development wave is down to a low right now, but it just means the developers are busy building all the important things. So there's much less theory to come out, much less pontification, just much more of
getting those users.
Yeah, exactly. Getting the
users and building dApps.
That's right. So it's a little boring. So there's not much alpha I can share right now because like
I think you dropped an hour and 35 minutes of alpha.
This was long. This was long coming. But beyond that, so now I just have to go back to just shit posting on Twitter. So
there you go.
Just build and shit post. That's all.
That's life.
Yeah.
Awesome. Well, thank you very much, Kevin. It truly was a pleasure.
Thank you. This was the first one that I've done in a long time. I think I did something very small recently, but this was very first one in a long time, precisely because every one of the other ones have not been particularly interesting to
I hope you enjoyed the conversation as much as I did.
I did.
So thank you.
Thank you.